this prepotential f of a or f of u on this complex plane that defined the that defined this u1 problem, that defined the low energy n equals 2 u1 problem, that described the low energy dynamics of this n equals 2 theory. Okay, and you remember that we already knew something about this f. You remember that we knew that in the semi-classical approximation, meaning at the one loop approximation, we had, where was that? Right. Yeah. We had f was equal to tau u squared by 2, or tau a squared by 2, plus there was this f1 loop which was I by 2 pi. This was tau cl, which was imaginary, remember. A squared, we'll call it, the Seiberg-Witten use capital A, so we'll use that. A squared log of a squared by lambda squared. Okay, this we knew. We also had motivated the definition of these two quantities, A and AD. Remember, AD was equal to del F by del A. Okay, and you remember that the duality map effectively permuted A and AD up to a minus sign. There was some minus sign somewhere. Okay, now before proceeding and discussing more about duality, we're going to look at a property of this prepotential here on the complex U plane. Remember that this prepotential, the one that I've written here, is valid only at large mod nu, mod nu. Okay. So now what we're going to do is to see what happens if we take u from this place which is large but completely imaginary. This is always the base point of our starting. You remember we decided we would always use our anomalous u1 R symmetry to set theta equals 0. Once theta is equal to 0, our coupling constant is purely imaginary. Okay, so our coupling constant here is purely imaginary, and this is going to be like a base point of our discussions, starting from here. Okay, fine. So what we're going to do is to ask, suppose we start from here, and then we go in a large circle around around infinity and come back. What has happened to A and AD? Okay, we'll first look at it in terms of formulas and then try to interpret this more physically. Okay, so the first thing we have to remember is that this is the U plane. So if we take a circle in the U plane, we've got a 2 pi I. What we've got is that U goes to U times e to the power 2 pi I. But remember, A was the square root of U. So this is the same as saying that A goes to A times e to the power pi I. Okay, which is of course A goes to minus A, but it goes continuously. Okay, so under this rotation, when we've gone from a point in moduli space and come back to the same point, okay, already we see that something a little interesting has happened, that A has gone to minus A. And if we kept just the classical part, so let's work out what A dual is. So A dual is equal to tau CLA plus I by 2 pi. Now let's first differentiate this. So we'll get I by pi A log A squared by lambda squared. And when we differentiate this, so we get I by pi A. Yes. Okay, if we just look at the classical part here. In the numerator, no, because it's a log. This is log of a squared plus log of minus log of lambda squared. So when we differentiate the log of a squared, there's no lambda squared. Okay, great. So note that the classical part of the coupling constant here also goes to minus itself as a goes to minus a. This business, this a goes to minus a, just classically, ignoring the one loop piece, might seem strange. It might seem that we've got some interesting effect even classically. But remember, a goes to minus a can be implemented by gauge transformation. What we did was to take our SU2 field and diagonalize it. We put it on the form a minus a. But this is exactly gauge equivalent to minus a by permuting the eigenvalues. Okay, so a goes to minus a was sort of nothing. We'll keep track of it because it happens in our representation of the problem. But it's like nothing. So classically, sort of nothing is happening. Okay, but let's write it down anyway. We have a goes to a, and AD goes to AD, so minus a minus AD. Okay, and then what? Now let's include the one loop quantum effects. Okay, so we've got this part is just doing AD goes to minus AD. It's the part in the log that does something new. Okay, in the part in the log, we have a rotating by e to the power pi I. Therefore, a square rotating by e to the power 2 pi I. Therefore, the log picking up an additive shift of 2 pi I. Okay, and now the I with the I gives a minus sign. The pi cancels pi, and we get a minus 2. This a is left over here, so we get minus 2a. This is clear? Now, we will represent these monodromies. We will represent A and A dual as the basis set of states on which SL2Z acts. Okay, we could have chosen other bases. We could have chosen NE and NM, for instance. That would be like the dual of it, or the inverse of it. Because remember, Z is NE times A plus NM times A dual. So if A and A dual transform in one way, NE and NM transform like the inverse. Okay, we could have chosen that, but we will instead choose this, just because Seiberg and Witten have chosen this. Okay, so A dual goes to, what did we get? We got, acting on this basis, we get minus 1, 0, minus 1, and minus 2 times A dual. Okay, so this will be our representation of the monodromy. How our low energy theory description changes as we do a loop around infinity. Okay, now I'm going to give you an interpretation, a physical interpretation of this monodromy. Okay, physically what is going on here? Look, what we are trying to do is take a to e to the power I alpha a and eventually set alpha around the whole loop equals pi. But we know a way of doing this in the theory. This is precisely the way that let me call this I phi. Okay. This is precisely the way our anomalous U1R symmetry acted on fields. In fact, if we did a transformation with the anomalous U1R symmetry with e to the power I alpha of that U1R, you remember that it acted on the scalar field with an e to the power 2I alpha. Maybe a minus 2I alpha, that I can't remember. And then acted on the gaugino and chiralino with e to the power I alpha. this is probably a -2, right? +2, I can't remember. No, +2, because you see, the original thing was -1 on the chiralino and +1 on the gaugino. And then we acted with +2 on both chiralino and scalar field to make it the same. So it's +2. Okay. So it acted like this on the gauge supermultiplet, on the chiral supermultiplet. Okay. So in particular, it acted on the scalar component of that, like e to the power 2i alpha. Now, therefore, we can implement this rotation by a U1R symmetry transformation if we identify phi is equal to 2 alpha. Now, we want a phi rotation of pi. Therefore, we want an alpha rotation of pi by 2, so that 2 alpha is pi. Now you remember that the anomaly coefficient in this U1R symmetry was 8. Okay? What does it mean that the anomaly coefficient is 8? What it means is that if we perform this U1R transformation, the Lagrangian is not unchanged, but it changes so that theta goes to theta plus 8 alpha, where theta is the theta parameter that appears in tau is equal to 4 pi I by g squared plus theta by 2 pi. Okay? So the anomaly coefficient here tells us that if I do a rotation like this, then that's equivalent, it goes to this, not quite the same theory. It's like not having done the rotation and working in a different theory, one in which theta has been shifted by 8 times alpha. Okay? Now when I go all the way around, so alpha is pi by 2, what has theta been shifted by? Theta has been shifted by 8 times pi by 2, which is equal to 4 pi. So the full rotation takes theta to theta plus 4 pi. Okay, great. Now you see, this is a symmetry of the theory, because theta is periodic with periodicity 2 pi, so in particular it's periodic with periodicity 4 pi.
So you're not going to a new theory?
You're not going to a new theory, you've come back to the same description. However, so then why, you might wonder, why has this monodromy had any effect? We've gone round, we've come back to the same theory, it should be the same low energy description. Okay? But remember, it's possible to come back to the same theory, but with all states shifted. This phenomenon is called spectral flow, and it happens quite generally in physics. So for instance, there's a simple example of this. Suppose you're working in non-relativistic quantum mechanics on a circle. Okay? We're working in a non-relativistic quantum mechanics on a circle, and you've got a charged particle on the circle. And you turn on a Wilson line around that circle. Now, because we've got this Wilson line, instead of all particles being, having the wave function coming back to, you can gauge away with the Wilson line at the expense of all the wave function having the boundary condition, not that the wave function is periodic as you go around the circle, but that the wave function as you go around the circle is equal to what it was times e to the power I times the Wilson line. This is familiar to you guys, right? Okay? Now, if you take the Wilson line and take it to 2 pi, once again you've become periodic on the circle. But notice that a state that had n units of momentum around the circle has been continuously transformed to one that has n plus 1 units of momentum around the circle. Because the effective value of n has shifted by 1. Okay? So once again, this is an example of an operation that is generically non-trivial, changes the theory. Turning on the Wilson line for a generic value changes the theory. But there's a special value in which it hasn't changed the theory. So you've come back to the same theory, but in the process of coming back to the same theory, you've rearranged states. The states that were labeled by some values of the label in the original theory are now labeled by other values of the label in the new theory. This phenomenon is called spectral flow. Okay? And this happens very generically whenever you do this kind of loop in theory space. Okay?
What happens to the vacuum?
In this theory, it only affects particles with electric and magnetic charge. So it leaves the vacuum completely unchanged. Okay? But in the theory you're talking about, if you think of n equals 0 as the vacuum sector, the vacuum is transformed to n equals 1. The lowest energy state, but in the n equals 1 sector. In the little toy example that I was giving you. Yes?
Quantum mechanics example that is the aiming DHE, right?
Yes. Would you like me to work out that quantum mechanics example in more detail?
Yeah.
Okay, let me work that out. Okay, this part we remember. We'll keep that part of the board. Okay, so the quantum mechanics example we're talking about is simply this. We have mx dot squared by 2. It's the we're going to make quantum mechanics based on the Lagrangian mx dot squared by 2. Simplest Lagrangian in the world to start with. We're going to change it a little bit. Okay? Simplest Lagrangian in the world with one little twist. X is periodic. So x is the same as x plus 2 pi r. Okay, still very simple Lagrangian. Okay. Now, before adding any Wilson lines, let's quantize this theorem. We quantize the theory in the usual way. We get a Hilbert space of operators, square integrable wave functions of x. But there is one catch. Because x was equal to the same as 2 pi r, the wave functions have to obey that. Okay? So we have that all wave functions obey that psi of x is the same as psi of x plus 2 pi r. Otherwise, it's the usual story. Now, this becomes more dramatic when we go to momentum basis. When we go to momentum basis, our wave functions are e to the pi p dot x. And the fact that this has to be true, okay? The fact that this has to be true tells us that p is equal to n divided by r, where n is an integer. Okay? So in the theory with no Wilson line, the Hilbert space is simply, the most general state in the theory is simply simply sum over n, a n e to the pi n by r. Okay, very simple theory. Okay, this is the most general state. Okay, now we're going to complicate this theory a little bit. We're going to take this, this is also true, x goes to x plus 2 pi r. And we add to the Lagrangian what we always do when we add a gauge field. That is, we add integral of a around x. We're adding a gauge field in the x direction. But a around x, when we write in quantum mechanics, we like to write it as a times x dot dt instead of a dx. Right, so we've added integral a, which we like to write as integral a x dot dt. It's the same thing. It's a dx. Okay? This, in principle, we could add any a we want. In this one-dimensional example, actually, all a's are basically equivalent because they're gauge equivalent. So we'll choose a to be a constant. All a's with the same Wilson line. Okay, so we choose a to be a constant, just some number. Okay? Now, let's take this number out. Now, how has the quantum mechanical theory been changed at all? Okay, let's quantize. So pretend you've gone back to undergraduate days, you've opened Schiff and you've decided to quantize this Lagrange. Okay, so Schiff or Dirac or whatever your favorite quantum mechanics book is, would tell you that the procedure is to work out the canonical momentum. So there's Px, which is mx dot plus A. Okay, so this is, let's call it pi x. Okay, then we're supposed to work out the Hamiltonian in terms of pi. Okay, Hamiltonian as a number doesn't get contributions from terms that are linear in x. Okay, so the Hamiltonian is just mx dot squared by 2. But we're supposed to write that in terms of pi. And therefore we write it as pi x minus A, the whole thing squared, by 2m. Now, why did we write the Hamiltonian in terms of pi rather than something else? The reason we did that is pi is canonically conjugate to x, and therefore is implemented by the differential operator d by dx. Okay, so the Hamiltonian concretely, meaning acting on wave functions, is, you'll have to help me, is momentum plus I or minus I plus I, right? Or minus I. D by dx minus A, the whole thing squared by 2m. This is the Hamiltonian. What? Now wait. Yes, exactly. Exactly. So now one way of thinking of this theory is as I've written it here. Wave functions continue to be single valued, but there is this A. There is another way of thinking of it where you gauge away this A at the expense of changing boundary conditions for wave functions. This is a singular gauge we're using, and let's not use it. Let's work in this nice regular gauge. Okay, so this thing here is n by r minus A. N by r minus A, the whole thing squared divided by 2m, acting on the nth wave function. Okay, now this is just a different Hamiltonian from A equals 0. Just different. However, we know on general grounds that when we do a gauge, when we turn on a Wilson line whose effect is 2 pi, ADX is 2 pi or 2n pi, we've done nothing. Okay? We know that on general grounds. These Wilson lines can be gauged away to nothing through a large gauge transformation. Okay? Because, why is that the case? It's the case because if you take an open Wilson line like this, it transforms like U under this and U inverse on that. Now if you take a large gauge transformation in general, it's not gauge invariant because the large gauge transformation has U here and U inverse here not equal to themselves. U is the gauge transformation parameter. So U would be a matrix. In UN theory here it's just e to the pi alpha. It's phase. So let's say that we've got a phase which was nothing here and e to the pi I phi here. That's why it's a large gauge transformation. Okay? But a large gauge transformation that acts trivially in the same way on all physical particles, okay, is actually a gauge transformation, actually a symmetry of the theory. Doesn't change anything. Okay? So if your physical particles all have charge integer, if this gamma phi comes back to itself up to 2 pi, okay, that hasn't changed anything. That's really a gauge transformation. But that changes my Wilson line by an addition of 2 pi. Okay, because it changes A by 2 pi. A goes to A plus 2 pi. Okay, so that it changes that Wilson line by that much. I mean, integral A, sorry, I said that wrong, but you know what I mean, right? It changes the Wilson line by shifting it by this 2 pi. Okay, so this A is a periodic variable. And its periodicity is such that any two values of A that have the same A times length of circle are actually the same Wilson line. Okay, this we know. Okay, but how do we see that in this formula? In this formula, the spectrum just looks different, right? So suppose now what I do is to take A times 2 pi r is equal to m. So A times 2 pi r is equal to m. Okay. So that tells us that A is equal to m by 2 pi. Now I'm messing up my 2 pi r. I'm messing up my, it's 2 pi m. Sorry. Okay, that's better. Okay, so A is equal to m by r. For any integer m, this has not changed the theory. What does it do here? So you see the spectrum says the same. The set of all eigenvalues of the Hamiltonian is not changed. But what eigenvalue you associate with which state has changed. Okay, this is spectral flow. This happens very often. Is this clear?
So even the set of states, set of eigenvalues, everything remains same, it's just the
It's just your labels. We just change the label n to n minus m, and then everything's back to the.
do you always get shift in a lattice type, or it can be, you can have different.
Yeah, in the examples I'm familiar with, it's always of this shift in the lattice sort, but there may be more. I don't see an argument for that. It could be more interesting. The reason that it's in the examples I'm familiar with is that the symmetries of the lattice sort. They're basically products of U1s, right? So you get the U1 lattice generated. Okay, if you had a non-abelian symmetry acting, then you could get something more interesting. I would have to think of an example. There probably exist examples. I suspect if you went and asked the condensed matter people next door, they'll give you 12 examples. Okay. Okay. Okay, excellent. This is clear? Now, the next question that arises is this. I brought this whole discussion up so that we can understand this formula. Okay? I'm claiming that the same kind of thing has happened. Theta has gone to theta plus 4 pi. Theory has gone back to itself. So, states have gone back to themselves, but the labels remain up. Now, notice that what has changed is A and AD. So, if A and AD have changed, NE and NM must have changed. Right? The thing that appears on the right-hand side of the supersymmetry algebra will not change when acting on a particular state, because there's one supersymmetry operator. So Z will not change. Okay? But remember that Z was equal to A and E plus AD and M. This you remember? Okay. So now if you're good at matrices, we can use matrices, or in this simple problem, we'll just plug it in. I'm going to move NE and NM, AD and AD by this quantity, and then ask what is the change in NE and NM. Okay? What change in NE and NM should I use? So let's say that what I have here is that A prime AD prime was equal to -1, 0, -2, -1. Okay? Now, let's put this in. Okay? So, what I want that NE prime times the new A, which was -A, plus NM prime times the new AD, which was minus 2a minus AD. I want this to be a NE plus ADA NE prime, NM prime. So I'll just collect factors of A. So A into minus NE prime minus 2 NM prime plus AD into minus 2 minus NM prime should be is identified. So this guy I should identify with NE, this guy I should identify with NM. And therefore what we're seeing is that NE is equal to minus NE prime minus 2 NM prime, and NM is equal to minus NM prime. Or if we want NE prime, well, let's do for NM prime first. NM prime is equal to minus NM, and NE prime I take minus is equal to NE with a minus sign, and then plus 2NM. Have I got that right?
Yeah.
I've got that right. Okay, excellent. Okay, so this is the transformation that acts on states. States which were labeled by numbers NE and NM have now become labeled by numbers NE prime and NM prime related by this boxed formula. Something confusing, Kanu?
The matrix, that thing is basically the transpose of the inverse of that matrix.
Yes, transpose of the inverse of this matrix.
From the right.
Yes, it's transpose because you have to act on the other side. Yes, so it's exactly right. And I presume we could check that, right, if you wanted to. Yeah. Okay. Perfect. Exactly. So now this is the thing that we want to interpret. How do we interpret this phenomenon? Well, this phenomenon has a famous interpretation. Okay, remember we already seen that what happens is that as we go from one to the other, theta goes to theta plus 4 pi. So what we must be claiming is that if we take theta to theta plus 4 pi, okay, this transformation happens on states. Now let us separate the trivial from the non-trivial. The first part is the minus signs, that is trivial. Why is that trivial? That is an effect not of theta but of something simpler. It's the fact that A has gone to minus A. Why does that change electric charges and magnetic charges with a minus sign? Well, it's very simple. Remember that the U1 part of the gauge field was the part of the SU2 part of the gauge field that was in the phi direction. Now, if A goes to minus A, what's happened is that phi has gone to minus phi. Okay? So we've just reversed the U1, the name for the U1 gauge field. When embedded in the full original SU2, what we are originally calling A, we're now calling minus A because we're taking the dot product not with this vector but with that vector. Okay? And therefore all charges get reversed just because we've changed the name of our gauge field to minus itself, therefore all charges will go to minus itself, both electric as well as magnetic. That is clear because electric charges are on the right hand side of del dot E and magnetic charges on del dot B, both have got reversed. Okay, so the minus sign is simply that phenomenon. This more or less triviality. More interesting is this 2m. Where did the 2m come from? The 2m came from this thing called the Witten effect. The Witten effect is the following statement. Okay? It's the statement that if you're working in a theory with theta equals 0, and then you change the value of theta continuously, okay, and then you change the value of theta continuously, then all states that in the original theory had magnetic charge start picking up an electric charge. Are you familiar with this effect? Is this familiar? Shall I explain it to you?
Isn't this the other way? Electric charge of the new one is picking up.
Yes. The thing that had magnetic charge is now getting an electric charge. You'll see exactly how it goes. Okay? Anything with a magnetic charge starts picking up an electric charge. Okay, are you more or less familiar with this or not? No. So let me explain it. It's a very simple thing. Goes as follows. Okay. Suppose that your Lagrangian, I'm going to explain it in U1. There's a similar phenomenon in a broken SU2 context, but let me try to explain. Suppose your Lagrangian was 1 by 4 f mu nu and plus theta. I will not try to get the numbers right. Okay, that requires Diksha to be present. She'll tell me how many pi's are there. Okay, I won't try to get that right. That's d for x epsilon mu nu alpha beta f mu nu f alpha beta. This is my Lagrangian. Now, once again, we're going to use, just like we did in our little toy example with the Wilson line. Okay, what I'm going to use is, what I'm going to do is to try to use canonical methods to find the generator, the charge that generates the charge that generates the operation such that every charge field phi goes to e to the power I alpha phi. Global charge rotations. Okay. So the way I'm going to do it is to think of this as sort of like a limit of a gauge transformation, one that is constant. Okay. So let's see. I hope I get this straight. So how do gauge transformations act on gauge fields? I mean, we should really be acting in the charge sector as well. Sorry, this phi. Sorry. Yeah. Okay, we should really be acting with the charge and so on. I'm going to just work on the gauge field sector. Okay, so how does a gauge transformation act on the gauge? How does a gauge transformation act on gauge field? Well, it generates del mu alpha. A mu goes to A mu del plus del mu alpha. Okay? How do I get del mu alpha? Well, you remember that E mu is canonically conjugate to A mu. Let me call that. The pi of A mu, let's say pi of AI, let's say. I'll work in A0 equals 0 gauge, just work with the spatial components of the gauge field. If I have pi I, the canonical commutator of that, okay, with A is delta function. So if I take pi times d mu alpha, pi mu, pi I alpha, E I alpha, this I is this AI, yeah. Okay, and I integrate. Then its action on the gauge field will be to shift with the di alpha as we expect, because we get a delta function, and integrating the delta function will give us di alpha at that point. Right? That's clear. Right? Or equivalently, alpha times del I AI. I'm keeping no signs, ignoring boundary terms mercilessly, all of that. Oh, I hope I'm. Boundary term is very important, right? Maybe I should not ignore the boundary term. Let me see. The boundary term maybe in this case is actually very important. You're right. So in fact, pi I ai is equal to 0 by a0 constraint. So the whole thing is just integral alpha pi ai dot ds on the boundary. Okay, so this will be the generator of the guy that makes these gauge transformations, because it's the generator of a compact symmetry. Okay, and then now what I will do is of course take alpha to be a constant. So alpha is out here. This pi a is integrated over the boundary, it generates this compact symmetry. Alpha is the same as alpha plus 2 pi. So this generator here, this quantity here has to have eigenvalues which are quantized in integers. Right? It's a statement that if the gauge transformation parameter is compact, charges are quantized. Okay, so that's great. Okay, so that's great. And now this this is fine, and this I will now presumably great. So this is a surface integral that gives me my charge. Let's say that this guy was 0, theta was 0. Now what is pi? What is pi I? Well, we take the canonical conjugate just from here. So this pi I, up to some factor of 2 or half, or I've got a 1/4, so no factor of 2, up to a minus sign maybe, is del 0 ai. A0 equals 0 get you. Okay, this is what we call the electric field. So this pi I was ei. And this E dot ds is exactly what we call the charge, so we're very happy. Okay, the generator of the symmetry is the charge. Okay, but now what happens when we turn on theta? Now this guy is a total derivative, but it contributes to the boundary term. It contributes to the canonical momentum. Okay, because there is a term here which is del 0 ai, and then fjk with the 3-dimensional epsilon ijk. So when I take the canonical momentum, I get pi I is del 0 ai, so it's ei, plus, so to speak, theta times bi. Okay, various 2 pi's have been murdered along the way. You look up Witten's paper. Witten in all his papers gets every factor of 2 pi right. In all his conversations he gets every factor of 2 pi right. So you can trust his 2 pi's. Okay. Okay. So now what we see is that the thing that generates these gauge transformations is ei dot ds plus theta times bi dot e dot ds and b dot ds. But the thing that generates a compact symmetry is always an integer. So this quantity is an integer. This I'm going to keep calling any. The constraint is still del I pi I equals 0. Yes, I think so, because you see, good question, because we're going to allow for magnetic fields. The constraint is still del I pi I equals 0. Let's check that. I think so, Because you see, once again, when a constraint is obtained from A0 equals 0 equation of motion, A0 equation of motion. That's why the constraint had the del I EI here. Because there was a del I A0 here and this stuff. But there's also, from here, a del I A0. So we will get del I with the new constraint equation now will involve the B term also, the full thing. Right? So it will still continue to work. Del I pi I is equal to 0, as should be, right? It should always be that the theory is gauge invariant. So the fact that del I pi I is 0 is the statement that the theory is invariant under gauge transformations. Can you see that? Let me remind you of that. You see, the thing that generates a gauge transformation with alpha is pi I integral del I alpha pi I. Now, if we ignore boundary terms with small gauge transformations, this should leave, it should act trivially on states. So it should be 0. So by integration by parts, del I pi I should be 0. What?
Pi I would be like something like del dot E and del dot B, right?
Yes, it's some combination of the two.
Yeah, let's say the B is 0, like the theta is 0 there.
Yes.
So del dot E is 0.
Del dot E is 0. But Sunil was asking, does it continue to hold when theta was not 0?
If it is del dot E is 0, that means charge is 0.
You see, what I should really be doing is adding the contribution to the generator from matter fields. Suppose I had a minimally coupled scalar here. I've been lazy. Suppose I had here plus d mu phi, the whole thing square. Okay? Now the momentum conjugate to the thing that generates the gauge transformation will also include, apart from the phi field. And that whole thing will be 0, even when charge is there. There it will become del dot E minus J0. That is always 0. Even though but not in a trivial way. It's a constraint, right? The fact that del dot E, in the theory with no charge put in, of course, del dot E was 0. In the theory with charge put in, del dot E is J0. But the constraint equation that is imposed quantum mechanically is del dot E minus J0 is equal to 0. So that's how it would work if you added the matter. Is that clear? Do you want me to work that out? It's clear, right? Okay. Excellent. Excellent, excellent. So where were we? So what we have concluded is the following. We've concluded that the guy that generates the symmetry is this linear combination of integral of E and the integral of B. Because it generates the compact symmetry, this is the guy that is the integer. Okay? It was an integer before. So under small changes, an integer cannot change. So this will be whatever the integer was that we called electric charge. So we'll continue to call it NE. Okay? In the old theory with theta 0, we called integral of B NM. But, you know, our prejudice is that electric charge is integral of E. If that is our definition of electric charge, where we conclude that QE prime is old QE plus theta times Qn. If our prejudice is that we define electric charge by integral E and magnetic charge by integral B. Okay? So, notice that this NE is a constant through this motion. Okay? And if we do this theta changing by a factor of 2 pi now, once again theta has gone to 0, it's actually gone to 2 pi. But you see electric charges have moved by 1 times old magnetic charge. Now it's a 4 pi rotation, so it's 2 times old magnetic charge, and I don't have the formula there anymore, but that explains that formula. NE prime was equal to, apart from the minus sign, plus 2 NM. It's there. NE prime is equal to minus NE plus 2 NM. Okay? So this effect on states is simply the Witten effect. Okay? So this is telling you, it's telling you how this theta shift is not completely trivial, but it's not completely non-trivial either, since it was just a spectral flow and involving just one loop physics. Okay? But it's a great thing. The great thing is that already one loop physics tells us that we cannot always work in a zero or monodromy sector. As we move along the moduli space, this AD column cannot come back to itself under every physical identity. Sometimes it has to change. Okay? So one change that's allowed is changes by shifts of theta and the corresponding Witten effect. This we understand very clearly, right? There's nothing mysterious about it. But it already has given us an SL2Z monodromy. Notice that this monodromy is an SL2Z. Okay? It's an SL2Z because all values were integers and the determinant is clearly 1. Okay? So, very good. Very good. So we've convinced ourselves that as we go down this U plane, our low energy description cannot be single valued. Okay? Has to come back to itself up to a monodromy. Okay. Now in the semi-classical theory, we have this single singularity at the center. And this monodromy would be, the same monodromy everywhere. I mean, there's no other singularity. The monodromy cannot change. Okay? So in the semi-classical theory, we've got this one singularity at the center. The monodromy cannot change. The singularity would be the explanation of that monodromy. And that singularity would just be the singularity that sets all that makes the theory deconfined. So the new massless fields, the gauge bosons of the SU2 gauge bosons that are not kept in our U1 description, the appearance of these new massless fields results in a singularity in a description dealing with only the U1 gauge fields. This is clear? Okay? Question: what happens quantum mechanically? Now, remember that we have this constraint. Remember that we had this constraint that we wanted our tau, okay, to be that we wanted the imaginary part of tau to be everywhere positive. Okay. Now, if there is just one monodromy all over the complex plane, we take out the point at infinity, we take out the point at 0, so this huge cylinder, there's a single monodromy, there's no non-commuting effects happening. Okay? Then Seiberg and Witten show that claim that a generalization of that old theorem, the theorem that if you've got an analytic function, then the imaginary part cannot be bounded from below, continues to apply. Okay? I haven't checked this out. That it continues to apply and guarantees that it's impossible in that situation for tau to be imaginary part of tau to be everywhere positive. Okay? So just property of complex analysis, that if you have just the same monodromy all over a cylinder and the cylinder is infinitely long, you will never be able to find a tau. Also there are some boundary conditions presumably in that statement. But I think just what's happening in infinity, you will never be able to find a value of tau whose imaginary part is everywhere positive. The old problem comes back to us. This is the claim. I would have to think hard about how one proves this in complex analysis. But since these guys are reliable people, I'm going to presume they're correct in their claim. Okay? Fine. So, motivated by that statement, they know that this structure cannot be the correct structure. unless this whole description is wrong. This whole U1 description is wrong. So the simplest modification of this is that, there's another singularity not near 0. But remember that our theory had a symmetry under u goes to minus u. So if the singularity anywhere other than 0. Okay, so one possibility, right, fine. If there's a singularity anywhere other than 0, there has to be a second singularity at minus of u. So by choice of holomorphic coordinates, we'll put this guy. So now this guy at 1 and this guy at minus 1. Okay. Now when I say u, it's just some holomorphic coordinate that agrees with trace phi squared infinity. And it's just whatever it is. Nice and analytic in the middle. I'll allow for analytic redefinitions of u. Okay, it's just at infinity the choice of coordinates has been done. Okay. Okay. So now this is their suggestion. Their suggestion is that perhaps the situation is such that there are two singularities in this theory. Now, if you want to make such a suggestion, you need a physical mechanism for generating these two singularities. Okay? And the physical mechanism they propose is a very simple one. Remember, we had these BPS particles in the semi-classical spectrum. Namely, we had W bosons, we had monopoles, and we had dions. I promised I'd tell you more about the dions, and I will. But for now, let's move on with them. Okay, dions are objects that have both electric and magnetic charge. And semi-classically, dions with 1 unit of magnetic charge and any number of units of electric charge exist. This we know by doing a semi-classical quantization of the classical monopole solution. I will explain this to you before the end of these Seiberg-Witten lectures. Okay, but right now let's not distract ourselves. Okay, so the idea that Seiberg and Witten had was that perhaps one of these particles becomes massless. Perhaps one of these particles becomes massless at one of these points, and another of these particles becomes massless at another of these points. Okay, this would be the claim that the n equals 2 theory. This would be the claim that the n equals 2 theory confines, because there is no point where the SU2 gauge bosons are becoming massless. That would be an unconfined behavior. So the idea is that this would be the claim, the idea that n equals 2 theory confines. Now, this is the guess we're going to make. The justification of this guess will come from the consistency, beauty of the solution, and later on people have checked that this is correct by doing by explicit computations of that f of a by summing the instanton series. You remember we talked about how we could find f of a if we could sum all instantons. People have actually done that. Remarkably impressive. You get the same answers. No doubt it's correct. Okay, so there's now a calculational method. You can forget the guesswork. But the guesswork is more beautiful and more elegant and more insightful than the calculation. So we'll continue with the guesswork. Okay. So now the question, what particles should become massless here? Now, W bosons becoming massless. W bosons becoming massless would be no confinement, because then you would recover all of the SU2. That is what we're saying does not happen. Okay? So now let us suspect that the simplest partner of the W boson, the simplest analog of the W boson, namely the magnetic monopole. W bosons are states that under the U1 are just electrically charged. You know, it's unlikely that very complicated states become massless, because complicated states are usually massive, very, very massive. So you would expect things with low charges to become massless, if at all. So the simplest state to think of is the magnetic monopole. Okay, so suggestion, Nm equals 1, Ne equals 0 becomes massless here. Let's make that suggestion and run with it. Now, There is one physical motivation for this suggestion. And I will give you this physical motivation before proceeding. In two minutes, unless somebody wants more details. The physical motivation goes as follows. A Tuft, in his deeply insightful work on confinement of gauge theories in the late 70s and early 80s, suggested a mechanism for how confinement might happen in QCD, which as far as we can tell is the correct mechanism, or at least one way of saying the correct mechanism. Okay? His suggestion went as follows. Suppose we're working in an SUN theory. We can always work in a gauge where some adjoint field, let's say trace f mu nu, not trace, f mu nu, is diagonalized. This is one scalar adjoint field. We diagonalize that. That's always possible to work in such a gauge. Once we've fixed gauge to such a gauge, that doesn't completely fix gauge. It leaves unfixed all gauge transformations that commute with diagonal matrices, and therefore u1 to the power n minus 1. Let's say we're working with un rather than sun, so we can stop saying n minus 1. Then that would leave unfixed u1 to the power n. So what Tuft said is, look, I've managed to abelianize the non-abelian gauge theory. By gauge fixing, I've made it abelian. Now this is sort of strange, because we know non-abelian gauge theory is very different dynamics from abelian gauge theories. So if you by some trick abelianize it, it almost feels like something wrong has happened. Can't be that this abelianization is perfect. Okay? In what way is it not perfect? It's not perfect in the following way. In order to understand this, let's work in SU2. Okay. In SU2, what we are doing is diagonalizing a 2 cross 2 matrix, a traceless 2 cross 2 matrix, because it's an adjoint field. Traceless because it belongs to SU2. But every 2 cross 2 matrix can be written as alpha I sigma I. So, and as you know, the eigenvalues of alpha I sigma I are plus minus square root of alpha squared. The eigenvalues of sigma is plus minus 1. Therefore, the eigenvalues of alpha 1 sigma is plus minus alpha 1. Then by rotational invariance, this must be true. So as you know, eigenvalues are this. Note the plus minus. Okay? So what we've done is diagonalize this thing. Now, where can we not diagonalize such a matrix? Where it becomes ambiguous to diagonalize such a matrix, where our gauge fixing condition breaks down, is when these two eigenvalues become equal. In this case, that only means it's 0. Okay? So in this case, when the diagonal matrix is 0, the question of diagonalization becomes ambiguous, because then you can do any gauge transformation you want, any SU2 gauge transformation, leave 0 equals 0. Had they been equal to some constant, that would still have been true, because leaves identity to identity. So same would have been true in U2 is what I mean. Similar analysis in U2. Okay? Now, that tells you that this gauge fixing works really well, except when all alpha i's are 0.
Why did the identity work?
We were working with SU2, so identity is not part of SU2. It's a traceless matrix.
Generator.
Yeah.
Okay,
Generator. Yeah. It's a gauge field. Right? Okay? So this gauge fixing fails when all alpha i's are 0. Now, how often do you expect that to happen? Well, inside the path integral, you take integrating over all values of fields, alpha 1 will be 0 on codimension, on some codimension 1 space in a generic field configuration, on a codimension 1 space in space-time. Alpha 1 and alpha 2 will be 0 on a codimension 2 space. Alpha 1, alpha 2 and alpha 3 will be 0 on a codimension 3 space. But a codimension 3 space in 4 dimensions is a line. So on a line, you expect this gauge fixing condition to fail. Now you can ask, what, suppose you manage to gauge fix to a and minus a, very similar to our discussion, right? We're gauge fixing to a and minus a. Suppose you manage to gauge fix to a and minus a. Okay? So you've got an effective U1 description. That was Tuft's whole point. Very similar to Seiberg-Witten's point. Okay? You've got this effective U1 description. Now, in this effective U1 description, what goes wrong? What is the description of these places where the gauge fixing fails? You can show the following. You can show that, in the neighborhood of this point, you can still do this gauge fixing. But the gauge fixing starts becoming extremely singular in the neighborhood of that point, as you approach that point. And you can show that what happens is that in that effective U1 description, what you have is a magnetic charge. That these places where the gauge fixing fails are locations of magnetic charges for this U1 description. Okay? And not hard to show. You sit down and do it, you will find. You will see this. It's basically trying to something that is in the neighborhood of this point where this is going to 0. You will see that there is this hedgehog type configuration of the gauge field. You're trying to diagonalize it. You can do that at the expense of one of these things. It's just because it's a simple 0. You'll see that if you try it. It's not a hard exercise. Okay? Oh, it's beautifully described in this book, Under the Spell of the Gauge Principle by Tuft. Okay? What is the point? The point is that once we've taken this SU2 theory and gone to this abelian gauge, we're still left with the U1 gauge theory, but with the U1 gauge theory with electric and magnetic charges. The electric charges were there in front of us because the original theory might have had an electric field, electrically charged particle. But the magnetic charges are unavoidable. They come as the places where the gauge fixing, the whirl lines of these where the gauge fixing fails. And in the path integral, these whirl lines will wiggle around everywhere, just like the whirl lines of electrically charged particles wiggle around everywhere. Okay?
This whirl line is that's the whirl line
of the monopole, magnetic monopole. Okay? So you see, the point is that it's true that there is a sense in which non-abelian gauge theories can be turned into abelian gauge theories at the cost of introducing magnetic monopoles. And this happens automatically through a simple procedure. It's nothing deep. You see? Okay. Now, a Tuft's sort of brilliant idea was the following. He said, look, I know of a place where magnetic fields are confined. It's a superconductor. Okay? If you take a superconductor and you take a tube which carries magnetic flux, as all of you know from your undergraduate studies, in the bulk of the superconductor, instead of the magnetic flux going all over space, it goes into a tube. This is simple physics. Simple physics that you can describe by studying the coupled equations of Maxwell and this condensate of the scalar field. Right, and then there are different kinds of superconductors depending on length scales of the scalar and all that I've forgotten. But this part is simple and beautiful. So, if you had magnetic charges in a superconductor, these magnetic charges would be confined. Because the first magnetic charge would be the source of one of these magnetic flux tubes, and the second one would be the sink for it. If you move them a distance d apart, that would create a magnetic flux tube of length d, and therefore cost energy d, and therefore would be linear confinement. So Tuft said, well, this is a consequence of having a vacuum in which which had a non-zero expectation value of electrically charged particles. Because that's what a superconductor is, right? It's a place where electrically charged particles, namely Cooper pairs, have a non-zero expectation value. But his point was, look, in this path integral I have both electric and magnetic charges. So by duality, if I get a vacuum with a condensate of these magnetic monopoles, that in the vacuum these particles are just running around all over the place. If I have a condensate of these magnetic monopoles, then by the same physics I'm going to get confinement of electrically charged particles, namely quarks. So this was his suggestion. His suggestion was, I cannot prove it, but my guess is that if you manage to do the path integral of QCD by, in the way I'm talking about, going to this maximally abelian gauge, then you will find that the magnetic monopoles want to condense. This is what leads to confinement. Okay? So this was a 10 minutes, I thought it would be 1 minute, but it's a 10-minute summary of Tuft's idea of confinement. Very simple, very beautiful, very deep as far as we know, correct. Okay? Now look, let's come back to our theorem. Please.
Is that if alpha 1 is 0, it's 4 dimension 1, alpha 2, if alpha 2 is 0, it's 4 dimension.
Alpha 1 and alpha 2, 0.
So why is that?
Why is that? So suppose I take a function, it's some function of position, and I demand that that function is 0. I'm in 4-dimensional space. That defines a mathematical condition, f of x1, x2, x3, x4 is equal to 0. Okay? It has a 3-parameter solution. If I have 2 such equations, it's 2 parameters, nothing more than that. Clear? Excellent. Now, let's come back to our theory. In our theory, we have very similar setup to Tuft. We have an SU2 theory. We've got this maximal abelian, they in a way are working in a maximal abelian gauge, not for all fluctuations maybe, but at least for the vacuum expectation. It's very similar in many ways. And they're proposing the theory confines. So if that is the proposal and if Tuft is correct, it should be somehow that the monopoles are light fields, not very heavy. Otherwise they can't participate properly inside a confinement mechanism.
Why is that?
Because heavy things don't condense.
Don't condense.
Right? So it's very natural, therefore, based on this, to suggest that one of these guys that becomes massless is the monopole. In these theories, precisely you can't have tachyonic masses because the mass of the monopole is governed by this supersymmetry formula. But we will see as we go along in these lectures that if we take this theory and deform it to become an n equals 1 theory, that n equals 1 theory we will see confines, as did this theory, but in the presence of a condensate of monopoles, because this guy becomes very massless at this point. So we will see more of this as we go on. Okay? Motivated by these general considerations. Or at least this is my interpretation of their motivation. They don't write it in these words, but I think this was a part of their thinking. Okay? Suggestion is that one of these particles that becomes massless here is the magnetic monopole. Okay? Then the second particle, well, we'll see. So let's start by studying the condensation. Let's start by understanding what happens if it's true that a magnetic monopole becomes massless. Okay. So let's see. Suppose it's true that a magnetic monopole becomes massless. What can we say about A and AD? What can we say about A and AD in the neighborhood of that point? Well, the only way a magnetic monopole can become massless is if in the neighborhood of that point AD is equal to 0, at that point AD is equal to 0. Because from the BPS formula, the mass of the magnetic monopole was AD. Okay? So, we are conjecturing that there is a point where AD goes to 0. Now, we can use duality to figure out the physics. We can go to the frame where AD was A, the gauge boson was the dual gauge boson, and now what we've got is an electrically charged particle becoming massless. It's an electrically charged n equals 2 hypermultiplet. Okay? So now we can proceed in two ways. Either we can A, do a one loop calculation, or B, figure out the answer from general considerations, which is what I'm going to do. The general consideration that will help us figure out the answer is this. Suppose A is not 0, AD is not quite 0, but almost 0, very small. Then we've got this I'm working in dual picture. So I've got the electrically charged particle, which is becoming very, very light. Now remember that the beta function for a U1 theory tends towards infrared freedom. So that means that the coupling constant is becoming smaller and smaller and smaller. Because the coupling constant is becoming small, the coupling constant can be reliably computed at near equals 0 because it's weak. So we can just keep one loop and ignore the rest. So just like we could compute the coupling constant, the prepotential at infinity, because the coupling constant was weak there. If we make this assumption that this magnetic monopole goes to 0 mass here, then we can reliably compute the coupling constant. We can reliably compute the coupling constant, the whole prepotential, but I'm showing you how, in the neighborhood of this point. Okay, so let's do it. What does it mean that it tends towards higher freedom? Well, it means that the coupling constant as you flow towards the IR under renormalization group flow goes to 0. QED beta function. Supersymmetric version of that, yes. In QED, beta function goes to 0, cut off by the mass of the electron. Right? In the IR. This is this famous problem Landau pointed out, that in QED the coupling constant blows up at finite energy if you trust one loop in the UV, but goes to 0 in the IR. Doesn't quite reach 0 because the coupling constant running stops at the mass of the electron. That's why we have electromagnetism. If there were if it just kept going, we would get 0 and then it would be a boring universe. Right? So I'm just going to write down what we can say about the coupling constant in this theory from the beta function. We can calculate the beta function, calculate the number behind it, because it's a charge 1 particle, n equals 2 supersymmetry. Okay, simple calculation. Plug into famous formulae and get the beta function. Beta function goes to 0 logarithmically. Okay, the coupling constant goes to 0 logarithmically, and when you write down, work out the formula with all numbers, you get tau d is equal to minus I by pi log of AD. Of course, we should say AD divided by some scale, lambda QCD. But we're ignoring that scale, just the dependence on them. Okay. Now, let's see if this formula makes sense. I never remember our definition of tau. Somebody remembers that, you should help me, but is it 4 pi I? Let me get the definition. Theta by 2 pi plus I 4 pi by g squared. Let me write that down. This is how tau is related to the usual coupling constants of the theory, the coupling constants which we have intuition for. So let's see what this says. This was tau is equal to minus I log of AD, but tau, we've set theta equals 0, let's say, okay, is I 4 pi by g squared. Okay, and therefore we have 1 by g squared is equal to minus 1 by 4 pi squared log AD. But as AD goes to 0, log goes to minus infinity. So 1 by g squared goes to infinity, and therefore 1 by g squared is going to 0 from the positive side. G squared is going to 0 from the positive side. As we expect, this was the infrared freedom. What? Coupling constant goes to 0. This is infrared freedom. Okay? So I've checked that this is going the right way, that we've not made a minus sign mistake. And to get the number, we have to do a more serious calculation, which is an easy one, right? Simple one loop calculation. Look up one loop results, because one loop results for any running of anything are unknown. So if you don't want to look up supersymmetric results, you can look up the results for non-supersymmetric theory and add them up in components. That's a simple thing, because we know the state content of a hypermultiplet. Any hypermultiplet. Okay, so now let's go back here and make this tau was equal to this. Okay, so by the way, how did we get this? What is the relationship between this and the beta function? Somebody? Why does beta function tell us dependence with AD? We've seen this many times, but just to make sure you understand. It's because the running stops at AD. Okay, so g squared at scale E is given by a beta function formula, but low energy g squared is given by g squared at scale AD. So you use the beta function to get g squared at scale E. So the beta function will tell you that tau at E is equal to minus I by pi log of E divided by lambda. That's what the beta function will tell you. But tau is just tau at AD, because the beta function stops running after the massive particle, and that was the mass of the of our dual electrically charged particle. Clear? Okay, so the logic is clear, right? This, we get the dependence on AD because AD was the energy scale in the beta function. You can do it more seriously if you want. You can do a one loop calculation with a hypermultiplet. It's not a big deal. You can do it and find it. Okay, but this is the answer. Great. Now, let's say that this is the point. This is happening at this point, u0, which is equal to 1, but we'll just say u0 for a moment. Okay? Now we know that AD in the neighborhood of this point goes to 0. So it's equal to, let's say, some alpha times u minus u0. Right, AD is a good smooth coordinate in the neighborhood of this point and goes to 0. Okay, so we've concluded that tau is equal to minus I. Maybe we should first integrate this. Let's get the way. Okay, let's do it this way. Okay, now yeah, okay, let's do it this way. Let's follow them and do it this way. So we put in this in the neighborhood of this point. So we get tau is equal to minus I by pi log of constant, which we don't keep track of, and u minus u0. Okay? Now let us remember what tau was. Tau in our original way of thinking, okay, tau was equal to del AD by del A. Tau is this. Okay, which we can write if we want as is equal to del AD by del U divided by del A by del U, because each of A and AD are functions of U. Okay, now we need to figure out that there you say, okay, so we know that tau is this. We know what del AD by del U is, that's alpha. Right, because AD goes linearly with U. Okay, so we just plug this in. So we have del AD by del U by del A is equal to del A by del U divided by tau. Okay, which is equal to alpha divided by minus I by pi log U minus U naught. Oh, that's a strange result. Del A by del U. Is that what they get? Just a minute. Nah, I got it ulta, right? Because this was tau of the dual theory. Remember, we got the formula where we pretended that the magnetic monopole was an electrically charged particle, and then got the formula. So we got that formula after doing an AD flip. Now remember that under the duality, tau goes to minus 1 by tau. Okay, so this should have been 1 by tau. So let me do it again. This quantity we should identify, this quantity here, we should identify with 1 by tau. Minus 1 by tau. Minus 1 by this tau. So minus 1 by minus I by pi log of alpha U minus U naught. Minus 1 by this is del AD by del U. Is the correct tau, the tau in our frame, which was del AD by del U. Okay, so this is equal to alpha divided by del A by del U. Now we've got a more civilized formula because we've got the log upstairs. Okay. Okay, and so we have that del A by del U is equal to I by pi log of, we can forget we want the singular part, U minus U naught. What? There's an alpha, but that's constant, because log of A, B is log of A plus log of B. Outside, thank you. There's an alpha. Okay, excellent. And now we just integrate this, so that's x log x minus x. The x is regular, throw that away. X log x. So we get A of U is equal to I alpha by pi U minus U naught log of U minus U naught. And then maybe some plus beta, some constant or some x value, doesn't matter. In the neighborhood of this point, this is what this A of U formula looks like. Okay, and let's write also what AD was. AD was equal to alpha of U minus U naught. Okay, so now we're in business. Now we can work out the monodromies. So what happens as U goes around U naught? u minus u naught picks up phase e to the power 2 pi I. Okay. So so u minus u naught picks up phase e to the power 2 pi I. So we have AD goes to AD. But A prime is equal to what? Well, we get a 2 pi I addition from here. So 2 pi I, pi cancels, I gives minus 1. So A prime is equal to, and then we get minus 1 and there's a 2. So A is equal to, A prime is equal to A plus 2 AD. Maybe it's minus 280. Let me think. Minus 280. Minus 280. Minus 280 because I squared is minus 1. Well, last time AD shifted. This time A shifts. This is sort of like the dual formula. Okay, now let me check if I've got, wow, we've got it all right, including the minus sign. So, okay. This is the monodromy of A and AD. Okay, and as Kanu suggested, you can now translate this to see what NM and NE are doing. And what you will find, obviously, is that NM is picking up a phase, is picking up a, is shifting, NM is shifting, whereas NE is remaining the constant. Then we'll find the dual of what we had last time. Okay, it's like the dual Witten effect taking place, something like that. Okay, excellent. So now we've got this this new monodromy matrix, which we'll write as 1 0 1 no minus 2 1. That's right. NM picks up a 2NE part. It's like the flip of the NE and NM. Okay. Notice that everything we've done here is reliable, because we were using one loop beta functions where they were reliable. Okay. Great. So now what do we know? We know now that if we take the complex plane, we get some monodromy here. We've represented that as a matrix. We know by sort of fiat, we've guessed that we get a monodromy here. We're starting always with this base point. So if I take this, and we know that the location of the other monodromy is -1. We've just said u naught is equal to -1 by a redefinition. It's like a constant scaling or something like that, the coordinate. Okay, so we got this monodromy, which we now want to break up in terms of these other two monodromies. But all we do is to make it this. Because of this base point here, it tells us which way to go. Okay, so it tells us we have to do this first and then this second. And so we see that M infinity is equal to this one first, so M minus 1 into M1. Okay, first this, then that is equal to M infinity. So this monodromy going back and forth to this base point must be equal to this.
This part is fine from that particular.
Yeah, but it's an operator operation. This is -1 and this is 1.
Oh, sorry, operator.
This is an operator, so acting on the right is first. Okay, and so we've got this relationship. Now we can use that to solve for m infinity for m1, sorry, m minus 1. We don't yet know m minus 1, but we can easily find it because we know m infinity as a matrix, we know m1 as a matrix, and we know how to invert matrices. So we can find it. I'm not going to do the algebra for you. Okay, let me just check. M-1, M1. Perfect. Yeah, they agree with that. It's M minus 1, M1 is the operator. Right. So very good. So they get the following answer now by just solving this equation.
What is M infinity?
M infinity is the monodromy around infinity. We worked that out at the beginning of the class.
Oh, that -1, 0, -1.
Yes.
Okay, that's the.
Right at the beginning of this class we worked.
And this is M1.
And this is M1. This is the one. So M infinity was the one from the one loop beta function. M1 was the one from magnetic monopole condensing, becoming light. Okay, so we can work out M minus 1. Okay, in fact, let's just to make sure we're getting it all right, let me just work it out, just to be totally. Somebody, please read out what M infinity was in M.
In the row, -1, 0 and -2.
And this 0 and -2. And M, I just rubbed it out, I'm so sorry. Can somebody write? 1, 1 and then -2, 0, right? Okay, so we want to find what M minus 1 is. Perfect. We want to find what M minus 1 is. So M minus 1 is equal to M1 inverse times M infinity. Now M1 inverse, let me make a guess for this and you tell me if it's right. Is this equal to, with some signs, right? 1, 2, 1, 0.
No, 1, 2, just the sign of the -2 changes.
Just the sign of the -2 changes. So plus 2.
Yeah.
Plus 2. Yeah, you're probably right. Let's check. I'm multiplying 1. Yeah, it's right. Perfect. Okay, so we get M minus 1 is equal to 1, 2, 0, 1 times M infinity, which was -1, 0, -2, 1, -1. Okay, and let's see. So here you get -5, and this is -2, and this is -2, and this is -1. Is that what they get? Oops. They get -1, 2, -2, 3. How have we messed up? Let me just check their M infinity. Their M1 was 0, 1, 0, -2, 1. Oh my God. Just a minute.
They are taking the AD first and A second.
Maybe they're taking AD first and A second. But why are they getting such strange numbers?
We should get the same numbers.
Numbers with some permutation, right? Let's see. Have we done this right first? Let's check. Have I messed up on some sign somewhere? Their infinity, oh, M infinity was minus 1, 2, 0, without a minus 2. That is the problem. Their M infinity was this. This is their claim. I mean, as you said, they mixed it up. Let me just work this out, and then we'll go back and try to check what we did wrong with the sign. Sorry about that. So they've got a plus 2 here. They get, okay, so this M infinity is plus 2. Okay. So then they get 3, then this would be 3 minus 2, 2 and minus 1. That looks sort of like what they have. Yeah, they have a 3, a minus 1, a 2 and a minus 2. Yeah, so they get this. Now where did I mess this one up? Just a minute. Let me see. They had their AD goes to minus AD plus 2A. We got a minus 2A, right? We may have messed up a sign. Let me work that out again. Okay. I'm sorry, I'm working this out once again. F1 loop was equal to I'll just check everything since we got something wrong. I by 2 pi a squared log a squared by lambda squared, correct? Okay. Now I'm doing a counterclockwise loop around infinity. I'm picking up okay, fine. This is a F1 loop. Del F by del A is equal to, I want this, so that's 2 by pi a log a squared by lambda squared. I'm picking up, yeah, so this definitely shifts by 2 pi I, so that's minus 2a. That's the problem. That's the point, right? So let's write this properly. We have AD prime and A prime was equal to minus A. Yes, minus A minus 2 minus AD minus 2A.
That should be plus 2.
2 pi I will multiply the I and there is an extra minus sign from the A. So that's why it becomes a plus 2.
But now it's a question of whether you're writing in terms of A or A dual. I mean, A prime. Yeah, I'm a bit confused. Sorry, just let me think about that. So, minus. Isn't this what we're getting if we write?
If you substitute A to be P power I pi times A.
Then that's an extra minus sign which we did.
You will get A, the new AD to be plus
2A, yes.
Substitute A.
Yes. You're right. Sorry, I messed up on that side.
So that is plus 2.
That's plus 2A. This is plus 2 here. And then everything works. Sorry about that. Okay, yes. Sorry about that. Excellent. Excellent. So the new singularity around infinity now has this monodromy in our language. I'm sorry that Seiberg wouldn't work with ADA. We are working with AAD. You'll have to transpose that if you want to compare. Okay, excellent. But we've got this. We've got this. The monodromy around the new singularity is this. Now, the next thing these guys note is the following. They note that this monodromy here, okay, this monodromy is equal to the following, okay, is equal to that there is, one can write the following: m minus 1 is equal to a m1 a inverse, where a, now I'm supposed to do what? I'm supposed to flip rows and columns, right? I'm going to try to do this flip and see if I can manage it. Wait, let me just check if that my rule is going to work with them. I'm going to have to interchange this and flip. Yeah. Okay. So A in our notation is 1 minus 1 minus 2 1. Claim this is the case. Okay. If somebody is brave enough to check, is there some mathematical whiz here who can immediately in 3 minutes in 1 minute get this? Okay.
First row checks.
First row checks are fantastic. So we'll believe it works. Okay, so this is the case. Now, why is that important? This tells you that the monodromy we're getting from minus 1 is simply a duality transform, some duality transform. The duality transform by this matrix, okay, is some duality transform of the monodromy we got from 1. But we know that the monodromy we got from 1 was due to some particle going massless, namely a particular particle going massless, namely the magnetic monopole. So this formula is telling us that the monodromy that we're getting from minus 1 is exactly the form we would get if the monopole transformed by this monodromy would go massless. Now we have to do this carefully, because NE and NM transform according to the transpose inverse of these matrices. Okay? So what we're supposed to do is to take the inverse of this matrix, take its transpose, and act on, at least in my language, on 0, 1. What are we supposed to get? This will tell us what the charges are of the particle that goes massless for the new singularity.
Okay, so for the any NN in the M minus 1.
What? Sorry?
For any NN in the M minus 1, this will tell us what are the values.
What are the values of once you see, because this is telling us that this monodromy is a duality transform of the old monodromy. Okay? So we just, if we follow through that duality transformation, we will figure out which particle has gone massless, or we will have a good guess for the reason for this monodromy. Okay? If we just guess that the thing that has gone massless is the one that is the transform of the monopole by this monodromy, that will be guaranteed to give us the right monodromy. Okay? So you work this out, and you get that this guy has nm equals, well, they do it the other way, so let me be careful. 1 and ne equals y minus 1. That works out. Perfect. Okay. So now we say that we have an interpretation of the second singularity. The second singularity is a consequence of the dion going massless. And now exactly the analysis we did for the magnetic monopole, the beta function, computing, blah, 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 is guaranteed to give us the right monodromy. It's just the same analysis after this duality transfer. Okay. So now this is our final picture. Our final picture is the following. We've got this U-plane. We've got these two singular points. We've got the, just one second, the monopole going massless here, this particular dion going massless here. And we've got semi-classical stuff happening at infinity. What we've guaranteed with this picture is that the whole thing works out, that the monodromies match up. Notice that these monodromies are not mutually exclusive. They don't commute with each other. Yes, the monodromy matrices don't commute with each other. It's some subgroup of that. It's gamma 2, but more or less SL2Z. Yes, some subgroup of SL2Z. Okay. Yeah, sorry, Kanu, I stopped you. What?
Chose M1 to be a monopole and that's why you got it dion at
Correct.
-1.
Correct.
But you could have done it either way, right?
Yeah. Now, you see, the monodromy here was something fixed. So, if we choose, let's say, a particle of mass 3, 5, if we make that guess, we would get a different answer. It's not clear that it would all match up. Okay? So, we're making a physical guess.
No, but I think
Of course, we could have chosen dion.
something like if I choose a monopole at -1, do I get it dion at +1?
You'll get, I think, a dion, but maybe with the reverse. Let's see. Yeah. So the question was whether it should be a +1 or -1. This is what you're asking. Remember that the monodromy matrices A don't commute and B have to be multiplied in a particular order. So I don't think you will get the same dion, but you will probably get a dion. Perhaps you will get 1, 1.
Only electric charge.
No, I think the sign of the electric charge might change.
No.
Try it out.
Simple.
I think,
Simple.
yeah, something that won't be physically very different. Right. Okay. Yeah, I suspect that will be essentially the same solution. If you choose a monopole here, you'll get some other thing, but essentially the same thing. Some transformation will take the two to each other. In fact, the transformation is likely to be the transformation that you get by doing sort of like half a monodromy. You see, because if I can invert this diagram, then the guy on the left goes to the guy on the right. Okay? Now this is sort of like working with a different base point. Yes. Which is the same as working, after doing a half rotation. It's like working with the pi by theta equals pi rather than theta equals 0. Okay. Interesting. I don't know exactly what you will get. Interesting. Check it out. Okay. And see. Excellent. So now we're almost done. We've reached the 2-hour unitarity bound, after which information stops flowing. Okay. So we'll more or less stop here, apart for 1 or 2 final comments. I know last class I promised we would do the fancy mathematics, but we'll have to postpone that to next class. Okay. Now, but I will just say again what fancy mathematics we do. What is our problem? Our problem is to find A and AD that have these monodromies, that are holomorphic functions of U, that agree with semi-classics, and are nowhere lead to an imaginary part of tau that is negative. Okay? The really lucky thing is this. You see, we called tau partly because, as we are going to see, we can associate this tau with a torus, with some property, roughly the complex structure of a torus. And mathematicians know of a way of fibering tori over base spaces in a way that ensures that this tau, in some way of looking at it, is always positive. Okay? So they have this way of doing it. Their way may or may not be unique, but using their way and some physics, we will basically find a unique way of doing this. Okay? And the end result of that will be an explicit formula for A as a function of U and AD as a function of U, or effectively of this F function, the prepotential, as a function of A and then therefore of U. Okay? So the end result will be explicit formulae for A as a function of U and AD as a function of U. And these explicit formulae, as you will see, will contain a fair amount of physics. Okay? So, but the physics, in a way the physics is over. We have now formulated the problem in terms of a well-posed mathematical question. At this point, you could hand your problem over to a mathematician and hope that the mathematician might be able to solve it. Now, since it's interesting mathematics, we will go through it. But in a way, the physics part of the paper is over. And actually, you can see, if you read the paper, have any of you tried to read the paper? You will see that section 6 is the solution of the model. Up to here, it's very, I shouldn't say this on camera, but anyway. Up to here, it's very beautifully, very clearly written for a physicist. Section 6 is very beautifully and very clearly written for a mathematician. They've suddenly switched gears. Now we've done the physics. Let's work out the problem. Cohomology, blah, cycle, blah, 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 all this kind of stuff we don't like to hear. Yeah, this section is full of it. Okay, we'll decode it in our language and figure it out. But you can see that in their minds also the physics is done. Now we're doing the mathematics. Okay, excellent.